Hello everyone, welcome to our talk. Today I would like to talk about a hybrid approach to scientific software package management on an HPC cluster. My name is Qiyang Hu. This is collaboration work with my colleague Shaoqing Huang. We both from UCLA Institute for Digital Research and Education. Our talk can be divided into three parts. In the first part, we've discussed about the challenges for managing software for an HPC cluster, especially in a research university environment. The challenges can come both from the traditional configure make many ways and from using some package management framework. In the second part, we will discuss some details about our practice at UCLA to overcome those challenges. And our talk will be ended by a brief discussion and a summary. So let's first start to look into the challenges first. According to our observation, most of the university-based clusters still manages their software packages manually. For here, manually, what I mean is like they're using some in-house script to install the software packages by configure make methods. It might be okay if some limited number of software packages to be managed, but the problem is that if the software packages become more and more, and the biggest problem is like what they call the combinatorial complexity. Here I borrowed some presentation illustration concept from the spec group. So I use an example for our UCLA environment. So we have over 400 of libraries, applications, and we have multiple architectures, multiple compilers, and multiple programming models, and multiple versions to be supported, to be installed. And it could be easily to bigger than 10,000 of combinations to be dealing with. And one of the biggest problem is that when the system admins or user support admins, so they want to doing some process like to keeping the deployment up to date or to support users for various usage problems, and the process become very time consuming and tedious, and also it's including like instructing the users to do their installation in their own user space. Another problem is like it's very hard for us to keep consistent over multiple persons or multiple team members, especially when we are naming the schemes or to design the tree structure of the software sets, and also to keep a consistent up-to-date documentations between like multiple groups and multiple system admins. In order to handle the combinatorial complexity problems, introducing a high-level framework to build, to install, to manage the software packages would be a very good solution. For here, framework can be understood as a package manager. And what I mean high level, it means to manage the software packages in a systematic manner. So systematic means they provide with consistent APIs to access automatic building tools. Like they can use the existing make, CMake, auto tools, and they can handle the dependencies and the various flags through the consistent APIs. Also, they can generate the module files for the end users and for the environment module systems, like for the LMOD. At the same time, the framework is supposed to be good to serve for system admins, HPC user support teams, and the general users, including developers and scientists. Currently, SPAC and EasyBuild are the two most common choices for us. At UCLA, we made a preliminary study and research, and because our UCLA environment requests more flexibility, and we consider like which one can provide the most coverage for our existing packages, and we finally select the spec, and so far it's working fine because it covers like 3/4 of the packages only using the spec built-in script. So we are very happy about that. However, During our practice to use the software management framework like SPAC at UCLA, we found a couple of challenges that I want to share in our talk. The first challenges is we found like they generate lots of seemingly duplicated copies of the installed packages. So seemingly I'm here means there's the same type of package with a minor difference between the flags or unnoticeable dependency differences. I would say that it's a natural consequence of systematic management for combinatorial situations, because you can imagine like a simple package name cannot contain all the information about every dependency or the flags. In SPAC, they use the solution like to append a hash code in every package name to make every package name as a unique name. I would say that it's a good solution, but it inevitably introduces a lot of confusions and very inconvenient for both system admins and users. So that's what I mean the first challenge. I will give you an example. At UCLA, when we installed about hundreds of packages, and if we can check that for the HDF5 packages, so they have a couple of versions that we generated for that. And all these versions have the hash code on doing that. And you can look into that, you can find that there's 4 HDF5 copies compiled under the GCC 8.3.0 and OpenMPI 3.1.5. And by the studying all of that, you can find so these 4 copies only have the minor difference. Either they have flags of fortune or not using fortune is having the HL, not having HL. They have the SZIB and not having SZIB. That's what I mean, like a seemingly duplication. So this is one of the challenges that we noticed. Another challenge during our practice for adopting SPAC in our UCLA environment is to redefining modulefile structures. We found it's non-trivial to accommodate our existing or legacy modulefile scheme. Although SPAC provides multiple YAML files to redefine a little bit about the hierarchical modulefile structures, it is still not flexible enough for us. In these two pictures, I showed with the modulefile structure that the SPAC can generate for us. At the left-hand side is a flat structure that is a TCLC-based simple structure for all the packages listed under the modulefile root. On the right-hand side is the popular hierarchical one, and you can see that SPAC follow the typical structure of core, compiler, and MPI structure under the root. And you may notice that all the compiler are actually embedded under the MPI structure. And the problem is that our pre-existing scheme don't want to doing that, and we didn't find any alternative way to redefine that yet. So that's our second challenge when using the SPAC. The third challenge for our practice in adopting SPAC at UCLA is from people. It seems like both system admins and general users to be very hesitated to move in to use the SPAC. One reason is that the people usually overwhelmed by the complexity controlled in their SPAC-ish way. I have to say that for the beginners, the SPAC has a very flat learning curve to step in. But as the situation becomes complicated and the learning can become steeper and steeper, and it requires a lot of deeper knowledge about the SPAC system. And that's actually scared people away to some extent. And this is part of the reason that people actually want to have a huge momentum and to keep working in their existing scheme or legacy work. Another point is that SPAC is still in a very quick developing stage. So people are cautiously waiting for further updates. So people thinking that maybe they can actually introduce more features, more wanted features in their later release. So people rather to wait. And the fourth point is that under the university circumstances, people usually are okay to tolerate with some suboptimal runtime performance. So that's all the challenges from the people to be reluctant to adopt the spec systems. And our thinking is, why not just at the current stage, why not marry the spec systems and the existing manually installed systems to make both of them work together? So we hope that our work can provide with a workflow which is scriptable as much as possible for the system admins, and also to provide with a clean package list presented to the end users. So that is our goal. Our central idea is to introduce a top management layer above both systems. In order to doing that, we have to keep the spec and non-spec system decoupled as possible as we can. So here's the diagram that is showing the structure that our system will work like that. So we want to separate it with our software libraries, the binaries, modulefiles generated with the two passes decoupled as possible as we can. And our main work would be merging the two both modulefiles to doing that. And during the process, we will take advantage of spec generated modulefiles a lot. And then we reshuffle and sort modulefiles from both systems. At the same time, we will introduce more controls to customize the presentation for user support needs. Our first step is to decide our desired modulefile structure used in our UCLA clusters. Here, I'm showing an illustration for what it looks like. You can see that the root here means our UCLA default end user module path, and we adopt the hierarchical structures, and it is different from the spec defined one. And in ours, we embedded the MPI structure inside the compilers. You can see that the module files is we follow convention from the TCL C-based module files, but we using LMOD instead. To hybridize the both module files, we first let the spec generate both hierarchical and flat structured modules. It is very easy to be done inside the spec because in the module.yaml, you can enable both modules by a simple line like this. After that, we can parse out all the package information from spec-generated hierarchical modules. All the information include the package name, package versions, name version of compilers used to compile that package, and the MPI related for the name version of MPIs and all the other important flags. And also we parse out the hash code that generated from the spec. And another information is the folder information, and the absolute passes for all the packages that are generated in hierarchical module files. The third step is to store all these information into an SQLite database. So the fields can be corresponding to what we wanted or our customized module files. And one of the key is we use the hash code as the index to find the corresponding the passes information from the flat structured modules, and we store that information as well into the SQLite database. Another important step for hybridizing module files is that we introduce JSON files outside of the spec. So that JSON files, we name it as apps.json, is to define our support range. It is supposed to get input from our system admins. So here I give a snippet example for what it looks like. So on the very top of the key would define the name that it want to present to the users. Let's say in the example, it can be Bauti2, it can be Bauti space 2, it can be about _2 or -2. And then inside of that block, so we defined with the name in the spec shown up, the name of the package is shown up in the spec. And then we actually listed the versions that we want to support it. For example, like it's like a versions and the compiler versions, and then we also define with the default version that which version should be default. And then we together with the apps.json file and the SQL database files both fed into our Python process. So the Python process can do the following tasks. The one is we want to convert our original TCLC based modulefile to LMOD, and then we prepend the module paths for maintaining customized hierarchies. So we also adding the families. The families meaning like either it belongs to a compiler or either it belongs to the MPI, and then we specify the default version of that. And the last step is we actually copy our flat structured modulefile to our destinations. Basically, we construct our customized hierarchical structures in our Python process, and then we copy the flat structured module files from the spec to the corresponding destinations. Also, not only spec, but also our manually installed or manually generated module file into the destinations as well. In a daily operational viewpoint, our UCLA workflow would look like this. Initially, the user will submit a request for install or build some package that they want through ticketing systems. Our system admins will get the ticket and know the request. Then they will log into some spec admin account and loading the spec and any other environment. So first step, what we do is to query the SQLite database to check if the package has been already installed. If it is yes, then they will check if this package should be added into the JSON file to cover for our general support range. If it is not found, it is not installed yet, so our system admin can have the choices to do whether directly go to the spec way or directly go to the manual install way. If we want to go to the spec way, so we will check if the spec list, running the spec list command to see whether the package already been available in the spec. If it is available, then we can directly run the spec install command to install via the spec. If it is not, we can write our own package Python script by running the spec create command to see whether it is succeeded by running the spec install command. If it is not, then we have to retreat back to the manually install way. So to manually install that, we were doing according to the package documentations and then install that, and then we have to insert our application information into SQLite database, and we have to manually write our Lua manually write the Lua module files, and then we will go into the JSON file steps again, and the last step would be to run the module filter, that Python script, to process the module files to make the module files in place. You can see that there are gonna be the two branches, and it's up our system admin's decision to see whether we rely on the spec or whether we keep our traditional way to doing that. The big strength for our approach is that we don't have to make too much commitment when introducing spec in our system. Instead of doing with an all-in step, we will feel much comfortable for doing it gradually. So here's the vision for our UCLA software ecosystems. Every piece of package will be built upon our set of 7 system libraries. And the blue block is the spec one. That spec can handle a subset of the packages. The gray and the green one would be the subset of software packages handled by the manually installed way, like a traditional way. You may notice that there's a boundary between these two. I would emphasize that the boundary is dynamic because as time goes on, we will expect a spec will release more and more improved features, and also our experience on the spec will be accumulated, and we hope that more and more packages will be handled by the spec as time goes on. You may notice that there's another, the third category is that named the pre-built binaries. So what I mean pre-built binary is some sub ecosystems in the Anaconda or R, because from the experience of our system admins and from general users, so that standalone ecosystem handle the packages pretty well. So we don't want to bother to handle that using a spec or any other manually installed software, that category. So we decided to make this one as the third category. But above all of these 3 categories, we hope that every module files will be handled by our unified and user-friendly module file systems, so that we can present with a unified, clean interface for the end user, and also consistent workflow for our system admins. Before ending my talk, I'd like to have a couple of discussion points to share with you. The first one is that I found that there's a trend to keep both the framework-based management and the customized manually installed software management coexisted. I would say that there is still a lot of HPC systems that has some pre-existing systems or legacy systems, and the people don't want to abandon for their existed work that easily. On the other hand, I noted that the spec provides more and more support for linking to external packages. So that's a good sign that the trend may last for a while. About our approach, I would say it again that our contribution is to introduce a top management layer to unify the different software systems, and it helps a lot for system admins to adopt the framework solution. And I would point out that our approach is general enough to be not limited to spec, and I would say that by a little bit modifications or customization works, it can be applied, same idea can be applied to the easy build as well. For our approach, there are a couple of possible future extension works. For example, like we can unify not only spec, but also manually installed system and pre-built, and also some containers. So we'd like to doing some study on that direction. And also we want our unified system to manage the environment settings that's similar defined in the spec and Anaconda systems. And also the JSON file that we introduce in the system can be used for the website documentation pages. So that's all about our work. You are welcome to check out our demo code by this link. And thank you very much for your attention. And please let me know if you have any comments or questions. Thank you.